The broadcast is now starting. All attendees are in listen-only mode.
Good morning everyone, and welcome to this, which is the 8th in our webinar series for 2015. I'm Tom Pritchard, who will your host for today's session, and I'll be introducing you to our speakers shortly and also rounding up at the end. Today's webinar is Introduction to LimitState Ring, and it should provide you with an overview of the theory and the application of our masonry arch analysis software, LimitState Ring. The main section of the webinar will run until approximately 10 AM UK time and will include about 5 or 10 minutes at the end for some questions. These can be posted at any time via the chat functionality that's present in the webinar interface in front of you. We do try to answer as many of the questions as we can, but occasionally we don't always manage to get around to all of them, so apologies in advance if we are unable to get around to yours. We do, however, follow up on any unanswered questions after the webinar is finished personally. We do have a mixed audience today. Some of you will have used the LimitState Ring before, some of you will be new to it. If you do have some specific questions regarding the software which may require a slightly more long or considered answer, please do contact us outside the webinar via info@limitstate.com, and we'll be more than happy to answer these in detail for you. So without further delay, our speaker for today is Professor Matthew Gilbert, who is the LimitState Ring Product Manager, and I'll now pass you over to him.
Thanks very much, Tom, and thanks very much to everyone who's joined us this morning for the webinar. Right, so just looking at the contents, what I'm going to do first of all is look in broad terms at masonry arch bridges, how they carry load, how they collapse, and then move on to look at LimitState Ring, some of the underpinning theory, and how we can apply it in practice. So basically look at some examples, and then finally wrap up with some recent developments and some conclusions. However, before I start the webinar proper, I'll just give you some background to LimitState, the company. This was a company set up in 2006, spun out from the University of Sheffield, and the main aim was to commercialise methods developed during the course of academic research. And the key thing that we can do as a standalone company is provide software which is easy to use and takes advantages of the methods that we've been developing in the university. And finally, what I should say is obviously we can provide full support for end users of the software. So in terms of the focus of the company, the products take on board the current landscape in the field of civil engineering software, if you like. So what we've observed is there are two types of software. There's traditional software, which is basically automated hand calculations, and we could be talking about automated in spreadsheets or in simple programs. And then at the other extreme, we have much more sophisticated tools, for example, based on advanced finite element, non-finite element techniques, for example. But there's a big gap between these two types of software. So what we're focusing our efforts on is filling that gap with what we would consider to be mainstream tools using numerical rigid plastic analysis. And in terms of applications, we could be talking about geotechnical applications, we could be talking about masonry arch bridges, which is clearly the focus of today, or we could be talking about, for example, reinforced concrete slabs. And that actually coincides with our current range of, our main range of products. So we have LimitState Ring for masonry arch bridge analysis. We have LimitState Geo for geotechnical analysis, and we have LimitState Slab, which is the sort of newest addition to our range for carrying out concrete slab analysis. And these tools are widely used in the UK and in over 30 countries worldwide. And just give you a taste of some of the companies that are using the software at the moment. This is sort of from our website, so this is A up to B, so you can see some big names, AECOM, Amy, Arup Atkins, Balfour Beatty, and so forth. Okay, so moving on then to the webinar proper. Masonry arch bridges, what do we know about them? Well, firstly, we know there are a lot of them around. We think there are over 1 million spans worldwide. We know that the vast majority of these bridges are now well over 100 years old. I mean, there are some exceptions, but that's generally true. Some 500 years old, or even many thousands of years old in certain parts of the world. And what we have to do as engineers is make sure that these bridges are fit for purpose, and that means that we need to assess the bridges regularly. Getting in the way a little bit of the process is actually some of the archaic terminology associated with masonry arch bridges. So I've labelled the slide here, which gives some of the key elements. So the key thing is that we have a masonry arch which is comprised of voussoirs. In the case of a stone bridge, then those would simply be a single ring of voussoirs. In the case of a brickwork arch barrel, we may have multiple rings of bricks forming that. We then, above that, may have backing material, which may be concrete or masonry. And then on top of that, we have backfill, giving us a level road surface. And the barrel spans between abutments and the particular name for the element on top of the abutment is skewback. So various elements which we need to be familiar with when we're reading the literature associated with masonry arch bridges. So first thing to ask is, how do masonry arch bridges work? How do they carry the load which is applied to them? Well, the most fundamental work in this field was carried out several hundred years ago by Robert Hooke. He showed that if you get all the voussoirs, or the stone blocks that you're going to use to construct a masonry arch with, and you suspend them from a weightless cable or chain, you look at the profile of that chain and you effectively invert it, or take a mirror image of it, and if you can fit that profile entirely within the thickness of the masonry in your arch, then he showed that your arch would stand successfully. And that's quite crucial, because it meant that you were able to, as an engineer, work out what the proper shape was for a masonry arch. Now, the key thing to note is there are many possible profiles or lines of thrust which satisfy that requirement. So we're showing some here, and that was also something that some 100 years later, in the 1840s, William Barlow demonstrated very nicely with an experiment. So what he did was he showed that if you had 6 voussoirs and you separated those by timber blocks, you could move all but, for example, the timber blocks which I'm highlighting, and the arch would stand. And you could effectively remove different arrangements of blocks and clearly demonstrate the multiplicity of these lines of thrust in a masonry arch. However, if you apply, for example, a external load at quarter span, and you gradually increase that load, then you'll come to a point where you can only just fit the line of thrust within the thickness of the masonry. And this limiting line of thrust is unique. And if you apply any more load, you will end up getting collapse. And here we can see the classic 4-hinge failure mechanism for a masonry arch. And here we've got, it's quite a rare example of an arch. It's not an arch bridge, but it's an arch where we've actually got these 4 hinges present, and to prevent the arch from actually collapsing, somebody's infilled the underneath the arch, so we can sort of see it hanging there pre-collapse. So the key thing that Hook's work showed us is the shape of the arch in relation to the pattern of loading is important, and it's something that when we're doing assessment we need to take account of. So in other words, if we don't record the shape adequately, or we model an incorrect representation of the shape of the bridge that we are dealing with, then we're going to get wrong conclusions. And what we've got on the screen now is an example where that happened. So this was a local authority bridge in the UK, where the diagram on the left is a pretty good representation of what's out there in the field. The representation on the right is what was modelled, which you can see doesn't really bear much relation to the shape of the structure on the left. And what the conclusion was that this bridge can carry no external loading before collapse. Clearly, because the shape of the arch is modelled incorrectly, the conclusions are of pretty much no value. So we focused on the arch barrel. There are clearly other things, very important things, which affect capacity. So in reality, we have an external live load, typically from a road or rail vehicle, and that will disperse load through the fill onto the arch barrel. And we also have the dead weight of soil, infill or backfill on top of the arch. And we also have potentially remote from the load passive pressures, which will restrain sway of the fill into the sway of the arch into the surrounding fill. And then there are other things labelled on this diagram that could occur: abutment movement, 3-dimensional effects, and so forth. So it's actually a relatively complex system that we have to analyse in practice. And in addition to that, we also have the potential for defects. So, for example, if you have a multi-ring brickwork arch, then there's a likelihood, certainly if the span is any significant size, and we're talking about standard lime mortar, for example, then we're very likely to get separation between the rings, and we're very likely to get a multiplicity of hinges forming in our barrel, which will significantly reduce the capacity. Also very common, if we look underneath the bridge, we very often will find that there's a crack close to the spandrel wall. We get a separation or detachment of the spandrel wall from the barrel, and very often we will find that the supports have moved slightly or not so slightly, as in the case shown at the right here, and we get distortion of the arch barrel. So it's important that we model in our analysis the actual shape of the bridge rather than the as-built or as-designed shape. Okay, so if we look at the range of tools that we can use to model masonry arch bridges, there have traditionally been a tendency to use very simple methods. So there's something that's used in quite a few countries worldwide called the Mexi method, which boils down to a simple, what's called a nomogram, where we just look up the provisional axle loading of the bridge based on some simple geometrical parameters. So that's one extreme. The other extreme, we can apply non-linear finite elements, discrete elements, and the like. In terms of limit state ring, it sits in the middle between those two extremes. However, what we've tried to do is to effectively allow it to be used as a very simple first level tool by using default parameters. So potentially it's easy, it's as easy or if not easier than the Mexi method in that respect. We've also tried to effectively move into the territory of the nonlinear finite element methods by allowing, for example, local properties to be set in the same way as you'd be able to do in using a general purpose FE tool. So we've tried to provide as broader or provide as much scope as possible to apply this to as many scenarios as possible. Okay, so just have a quick look at how the software limit state ring actually works before we get into actually applying it. How does it differ from other tools? Well, we use mathematical optimization to home in rigorously on the critical failure mechanism and corresponding collapse load of the structure. We've spent a lot of time validating the software against test results. And lastly, as I touched upon before, we have a user interface which allows you to very quickly get an idea of the likely capacity of a bridge, or to carry out a more detailed analysis using locally varying properties. Software is mentioned in various industry publications. So, for example, UK publication Syria Guide C656 talks about the method that's used by the software as being a very versatile tool and significant improvement on the more basic limit analysis formulations that we were pioneered in the 1980s and before. In terms of how it actually works, what we do is we assume live load is dispersed through the fill onto masonry blocks. Those masonry blocks are separated by contacts, and the contacts are actually where a lot of the interesting stuff happens. We can model there potentially sliding, hinging, and also crushing of the material. And then movement of the arch barrel into the surrounding fill is restrained by self-weight and also by backfill elements that we can see here in blue in the diagram, as you can see. And in terms of what you see on screen, we've just got a labeled view here. So additional elements here are the line of thrust, which is shown in blue. It's actually a thrust zone, so when you enter a given compressive strength of masonry, then the thrust zone will visually indicate what thickness of masonry was required to carry that magnitude of thrust. And we can see the hinges shown in red. We can also see that we have backfill elements that are highlighted in blue where those are actually being mobilized, and they're in gray when they are not being mobilized. And the way it works is that the software models passive resistance, but it neglects active pressures, which are generally very small in comparison. And then we've also got other elements. So, for example, a surface fill can be modelled separately with a separate angle of dispersion, and then above that, the axle. So how does it actually work? How does it find a solution? Well, if we go back to those slides that I showed earlier, but just think of it in a slightly different way. We know there's a multiplicity of lines of thrust in the masonry. Each of those lines of thrusts corresponds to an equilibrium state. We know there are many possible equilibrium states. For all those equilibrium states, the software uses optimization to find the one that corresponds to the maximum load factor. And that also corresponds to the point at which the structure will collapse. So from the point of view of the fundamental theorems of plastic analysis, we're using the lower bound theorem. We're maximizing the load factor, or adequacy factor as we call it in the software, finding the maximum adequacy factor subject to equilibrium constraints. And that also corresponds to the minimum upper bound load factor. So therefore we have the exact solution according to plastic analysis for the given discretization of blocks. In terms of the mathematics, how does it work? Well, if we look at a given block in a masonry structure, so we've got one that's highlighted in light blue, what we're doing is we are looking at equilibrium of that block. So equilibrium in the x direction, the y direction, and in the rotational sense. In terms of the forces acting, we've got self-weight forces acting. We've also got forces at the contacts acting, so normal, moment, and shear. And we also impose constraints on those contact forces. So what we make sure is, for example, that the shear force is within limits, being plus and minus the coefficient of friction times the normal force, so that we guard against sliding failure. Similarly, if we've got infinite compressive strength, then we can limit the moment according to relationships shown directly above. So the moment is between plus and minus the normal force times half the thickness. And the nice thing about it is, from a mathematical point of view, it's a really simple linear optimization problem. The other thing that we've as well as developing formulation, which hasn't been used by others certainly in publicly available software, we're also focused a lot on validating the results. So, for example, actually the very first version was developed in parallel with a program of tests carried out in Bolton in the UK in the early 1990s, and we tested a variety of single and multi-span bridges, and you can see a couple of them in the image below, and you can see output from a very early version of Ring above. And in terms of the correlation between the tests and the software, it's pretty good. These bridges shown on the table, 3-1, 5-1, 5-2, and multi-2, all have spandrel walls which are built outside the width of the arch barrel in order to remove, at least to some extent, the effects of the spandrel walls. 3-1, the ring analysis is 82% of the experimental load. 5-2 is also 80%, multi-2 is 100%. So bang on in terms of the analysis versus the experimental result. There's one slightly worrying one, which is 5-1, where we actually overestimate the capacity of the bridge. And the reason for that is this particular bridge was constructed using 4 rings of brickwork, and at 1720 kilonewtons we abruptly had separation of those rings, whereas the ring analysis assumed effectively we have a voussoir-like behaviour. And that's one of the unfortunate aspects of the multi-ring arch bridges is it's very difficult to predict when you will get debonding of those rings. In fact, bridge 5-2 is exactly the same as 5-1, but with those rings debonded artificially. So we actually put in effectively damp sand between those rings. And in that case, you can see we got a good estimate of the capacity. The only downside is clearly it's significantly lower than when we have bonding between the rings. One of the issues with those Bolton tests was that we had spandrel walls which obscured our view of the fill, and also there will be some frictional restraint between the spandrel walls and the fill, which is difficult to quantify. So more recently we've worked with the University of Salford to effectively carry out a new program of tests, which is ongoing actually, and what we find is that we get much closer correlation between the results from those tests because we're able to actually have a purely two-dimensional test in the Salford rig. And you can see in the next slide an image showing that rig. It's basically like a large fish tank, and we have special measures to make sure those side walls are very, very stiff laterally, but also frictionless. So the side walls are effectively frictionless. So we have effectively a section of a very wide bridge that we're able to physically model, which corresponds almost exactly to what we model in LimitState Ring, which is two-dimensional software. And then lastly, just before we move on to applying the software, just say that we're also doing smaller scale tests at Sheffield. Some of these are shown here, which are quite interesting because what we're doing is we are isolating each of the effects that contribute to carrying capacity. So for example, in the first row, what we're doing is we're actually bagging up backfill material on the side remote from the load, and so we've just got self-weight. In the next one down, we actually also have passive restraint, and the next one down, we also have fill on the left-hand side. And actually, we've got 6 or 7 combinations, and in each case, the ring prediction was within 10%, which I think is pretty good. So we think we've got a model which is reflecting the two-dimensional behavior of masonry arch bridges pretty well in the case of LimitState Ring. Okay, so let's move on to the software. When you open the software, what you'll find is that there is a new bridge wizard which allows you to very quickly and easily create a bridge model with the sort of the general characteristics that you're interested in. So for example, let's model a highway bridge. We can enter in the first dialog other details, but let's just leave those as the defaults for now. And then we move on to the geometry definition. So what we can do is we can explicitly define an abutment. This is particularly for end standing abutments where, for example, we may have a beam span adjacent to the end of a multi-span or a single span masonry arch. For now, I'll keep that default, so I won't model that abutment explicitly, and I'll move on to definition of the span. And what we can choose is a variety of different ways of defining the geometry. So the most general of those would be the user-defined interpolated option, where we would need to have a good number of points to define the profile of the structure, and that's certainly going to be the best thing to do when you've got good data from your field work, when you're doing your bridge inspection and etc. If you don't have that information available, if you want to do a preliminary analysis, then you can use, for example, the segmental shape if that's the closest match. And the other thing to say is we can choose how the barrel is constructed, whether that's a stern voussoir barrel, bonded brick, or whether it's multiple rings of brickwork which are assumed to be debonded. For now, I'll just keep the defaults, but what I'll choose is to insert a span after this, because I'm going to be modelling a multi-span bridge. This then gives us the pier dialog, so we can choose to model the I've changed the height of the pier clearly, the thickness, number of blocks, and also whether there is backing material above the pier as well. For now, I'll keep things simple and move on to the next pane of the dialog, which brings me to span 2. By default, whatever I entered in span 1 will be entered under span 2, and I'm happy with that in this case. Let's suppose we're modelling a 2-span bridge, so I can then just click next, which then brings me to the right abutment, and you can see actually we've got an idea of what our structure is going to look like as well on screen. And I'm not going to model an abutment explicitly, so I'm brought straight on then to the fill profile. And what you're able to do here is prescribe a piecewise linear idealization of the fill profile, and also to define a surface fill depth. Now this is very useful when you've got a surface fill which is different in character to the underlying fill material. So for example, if you've got a road construction with blacktop, road base and the like, you may want to model that separately. For now, I'm just going to keep the defaults, which is going to bring me on to the next area of interest, which is partial factors. Now, different assessment codes have different approaches. The simplest thing to do is to keep all the partial factors at unity and work with a global factor, which was a sort of traditional approach. More and more, however, limit state principles are being applied, in which case you would apply the relevant partial factors in this section and interpret the output from the software accordingly. Moving on then to materials. Initially we asked to define the masonry materials. What we can do is we can choose to have different material properties for the spans versus the piers and abutments, or we can choose global parameters for all elements within the masonry. And amongst the parameters that we're asked to define is unit weight, compressive strength, and coefficient of friction. And generally the defaults are reasonably realistic, if slightly conservative. So we have unit weight of 20 and a compressive strength of 5 newtons per millimeter squared, or megapascals, and the coefficient of friction of 0.6. Moving on then to backfill, we're asked to enter the sort of basic geotechnical parameters, and these are very conservative really. Angle of friction of 30 degrees, cohesion of 0, and a unit weight of 18. And we're also asked, do we want to model dispersion of live load? The default is yes. Do we want to model passive pressures? And the answer by default is yes. Moving on then to surface fill, we can enter different unit weight and also different angle of dispersion of the live load. If we have, for example, a particular detail near the surface which is going to broaden that angle of dispersion, we can enter it here. And then finally, move on to the loading dialog, where we can choose, for example, vehicles from the database, or we can define our own vehicles and enter them into our own database. So for now, I'll choose, for example, to import into my project an EU double axle, which has two 88 kilonewton loads, 1.3 meters apart, and I can choose to use that in my project, and it appears when I click finish. So I now have my structure defined, my loading defined, and if I click the green button, then what will happen is that the software will try to find the multiplier on that prescribed vehicle load in order to cause collapse. And what we've got here in this particular case is a factor of 3.3. So in other words, those axles need to be multiplied up by a factor of 3.3 in order to cause collapse. Now, what I haven't done is verify that my axles are at the critical position, and what I can do is I can move the axles around and see how sensitive the bridge is to the position. Actually, it looks like the initial position is was pretty good. I've got perhaps a slightly lower value, 3.32, but it's pretty close. So personally, I quite like to be able to move the vehicle manually and to explore my structure and the different failure modes that are predicted. And you can see that the critical failure mode is involving rotation of the pier, but that actually single span failure mechanism isn't very different in terms of the load factor. What I can do if I want to automate the process of finding the critical load position is I can actually choose to add load cases. So if I add load cases, and for example I add, I don't know, 19 load cases at a spacing of 200, and then I click solve, and what will happen is it will move across the vehicle across the bridge, and it will find the most critical one. And I can also see how what the outcome of loading at different positions were. So that gives you an idea of how quickly you can set up and solve a bridge problem, assuming that you have quite general information about the bridge. What I'm going to do now is I'll just delete all those load cases apart from the current one. I'm going to go back to the mode of exploring the behavior of the structure manually, because it will allow me to get a quick idea for how some of the other parameters that we could set will influence the behavior of the structure. So what I haven't done yet is talk you around the program itself, and what you can see in the right hand side is something called the property editor, which is very nice in allowing you to get a particular view of what's going on locally in the bridge. So for example, if I solve again and I click on the contact at the bottom, I can see that I've actually got values for normal force and shear force and moment at that contact. In advanced analysis, I can also do things like set local properties. So what I can do, for example, is I can select, for example, the bottom 5 contacts, and I can say, okay, this is a bridge over a stream, and I can see that there's mortar loss due to erosion effectively, and I can set that mortar loss to a particular value, say 100. And that allows me to change the effective thickness of the pier in those locations, and I can solve again, and I can see that that's affected also the failure mechanism of the structure. And it's also reduced the adequacy factor from, in this particular case, 3.4, where it was for the particular load position before, and it's moved that down to 3.12. So you can use the property editor to define local properties and get a potentially a more realistic representation of the structure that you actually have in the field. Okay, so let's just go back to the presentation. So the next couple of slides basically just reinforce what I've said. There's 2 modes. One is using the wizard to get a quick assessment, and the second mode is to perform a more detailed assessment defining local properties. So for example, in this case, again, locally selecting areas of mortar loss. One thing I haven't touched on is the output. So the report you can obtain very easily using the software. So after you've done an analysis, you can view a report. You can actually edit that report if need be, but the report will contain all the details of the input parameters and also details of the output, including very detailed information such as the forces at every contact in the structure. Further examples, I mentioned multi-ring arches are potentially problematic because they can give rise to different modes of response. And one of the things that Ring was designed to do from its inception was to model these scenarios, so you can see the output from analysis in the screen view on the right, and you can see that we've got hinges in each individual ring in that particular case. Also in that analysis you can see that we're performing a railway analysis, and the software was developed, or the versions 2 onwards of the software at least were developed in close collaboration with railway administrations to ensure that we model railway loading scenarios according to the standard rules. So for example, splitting the load between a sleeper directly underneath an axle and also the adjacent sleepers. I've just got a errant text there, just remove that. Multi-span arches. Now, one of the things that you may see in an assessment code is edicts such as you only need to model a multi-span as a series of single spans if the piers are stocky, i.e. the width in relation to the height of the pier is great. Now, what I'm going to do is just open up an example where that isn't necessarily a sensible thing to do. So this is a model of the bridge that you can see in the slides, and what we have is very stocky piers, as you can see, and what we also have is backing material above the piers. And what I'm going to do is I'm going to solve this problem, and what you can see is that the critical failure mechanism involves the central span, but also an adjacent span, despite the fact that we have no movement of the pier. So what the message is that actually if you had modeled this as a series of single spans, you would have had an overestimate potentially of the true capacity of this structure. Modeling this as closely as possible to what you have in the field is likely to be a much more sensible approach, and that allows you to pick up on mechanisms such as the one that you can see here, where we've got 4 hinges forming in the loaded span. We've got effectively force being transmitted above the pier head onto the adjacent span, which then also has a 4-hinge mechanism. And that we can see that here. So just give you a quick rundown on some of the more recent developments of LimitState Ring. So software itself has a heritage back more than 20 years. Research version, as I mentioned earlier, was developed in parallel with a series of tests performed in the laboratory, and there was 3 papers describing that work published in the Structural Engineer. We then developed a public version sponsored by Network Rail in the UK, and in the 2000s developed from scratch a new version in collaboration with the International Union of Railways, UIC. And the latest version was released in 2014, LimitState Ring 3.1. It brings, it builds on the developments in version 3, which is sort of more definition of arch profiles, faster solver, ability to add reinforcement, various other enhancements. 3.1 specifically allows us to solve larger problems than before. So we've got a bar chart here which shows that we can solve problems, for example, 4 times as big. Also, we've got a 64-bit version available. So if you've got a machine running a 64-bit operating system with a nice chunk of memory, then you can solve very, very large problems. And finally, for multiple load case problems, we've speeded things up so you can solve those problems more quickly. Okay, so wrapping up then with some conclusions. LimitState Ring is a rapid yet powerful tool. We can automatically identify modes of failure, whether those involve sliding failure, multi-span failure, including non-standard multi-span failure, as we've just seen. We validated the software against a wide range of lab tests, and as I mentioned now several times, 2 usage modes, 1 using default parameters for a quick assessment, 2 using detailed knowledge to define local properties to allow you to get a very good structure-specific indication of the likely mode of response. Okay, so that wraps up the main part of the presentation. I'll throw it open now to questions. So if you've got questions, if you can just enter those in the chat box, in the text box. Okay, just give you a few seconds to write those questions. Okay, so got a question coming in. Does the software allow us to define our own loading? Yeah, thought I'd mention that. Apologies if I didn't. So to define your own loading, we would go to Tools, Loads, Vehicle Database, and what we can do is add a vehicle directly. So I can say, my new vehicle, and basically I can enter details of that vehicle. So for example, loaded length, say 300, width 1800, and I can add as many axles as I want. So I'm just entering details of a possible vehicle here. Let's just put I don't know, I'll put something asymmetric so we can see exactly what that's going to look like. So I've got 3 axles, one with 100 kilonewtons, one with 80 kilonewtons, one with 120 kilonewtons, and there's a spacing of 2 and 3 meters between those. So if I click OK, I can then apply that, and it's asking me now, do I want to change this in all load cases? I can say yes, and so now I've got my new vehicle on my structure. What I'll do actually is I'll just if I go back to loads, I'll just delete the other load cases, so I can just traverse this across the structure, and we can see exactly how the structure and new vehicle are going to interact with each other. The other thing, actually, this is shown quite nicely, is in particular mode, the thickness of the line of thrust varies, and that's because we have and it's reflecting the amount of material required to carry the thrust at any given point. Okay, let's see. Just looking at the question box. Okay, so got a question, trying to see if I can understand what it means. Can I model settlements? Yes and no. What you can do is you can try to diagnose the likely effects of existing cracks. It's something that we don't cover in our standard webinar, but I can perhaps just do that quickly. So what we can go to is a support movement mode, and what we can do is we can effectively settle a block. So I can, for example, move down one of my piers, and I click solve, and what we'll have is a mode of response. And so we can use the software to diagnose the likely causes of existing cracks. Now, we can also run a vehicle across the bridge to see whether those cracks move around and the action of the vehicle, and see whether that's likely to lead to opening and closing of voussoirs and hence the damaging effects. However, if you've got large deformations and you've got a distorted profile, then the best advice is to survey that accurately and get that real geometry into the model. Okay, I think we're running out of time, so I'm going to pass back now to Tom just to wrap things up.
Thank you, Matthew, and thanks to everybody for listening. As Matthew said, we're now near the end of the webinar. We do hope you found it informative, got something out of it today. For people who are current users of the software, we do hope you found something new that you maybe didn't already know about it. And if the webinar has prompted any questions, then do get in touch, as I said at the beginning, via telephone or via info@LimitState.com, and we'll be more than happy to help you. For people who aren't current users of LimitState Ring, we will just get in touch with you over the next few days to try and get some feedback, find out if you have any further questions about it and whether you think that the software might be useful for you. Everyone may also be interested to know that we do have quite a large number of forthcoming webinars covering all the LimitState product range, some of which will focus more on particular problem types and applications. So please do look out for the event notifications that will be sent out via email and also posted on our website at www.limitState.com/events. So again, I'd like to say thank you all for taking the time to join us this morning, and I hope to see you all again for one of the future sessions. Goodbye.